So folks, Alex here. So one of my previous videos, I've implemented something known as Peano numbers as a kind of purely Rust type system entity, right? And if you haven't seen that video, you can go check it over there. I think it's pretty neat, but you know. Today I figured that, that implementation might not be like nerdy enough for that channel. And I decided to implement a fully fledged kind of stack-based programmable calculator within the Rust type system, right? So let's see how it works. So I'm trying to implement something like this. So VM state and stack and instructions pointer. And of course, all that is phantom, right? And load that code, right? So what is stack-based virtual machine, right? So it's a virtual machine. It's a computer, right? That operates on that stack, right? On that stack. And that stack is basically like exactly what you know and love, right? First in, first out thingy. Uh, and as I said, that machine will be like programmable, right? So we'll be needing to come up with a representation for our kind of opcodes, operation codes, and for a kind of some kind of container with those for those opcodes that we will be calling program, right? And in order to know where are we within that program, we will be needing that instruction pointer thingy, right? So let's see what stack is. So I want to model it as this, right? And of course it's phantom as well. So I cannot do anything like vec or slice or something like that, because these only get values when in runtime, and we won't be doing any runtime here, right? It should all that should work in compile time, and even stricter, it should work in the kind of type check part of that compile time, right? So the stack is this, and S0, S1, S2, and S3 are basically like the slots within that stack, right? So initially that stack should be empty, and it's not like this stack is missing, right? It's more like every slot should be tagged with that empty type to indicate that it's empty, right? So the initial state should be empty, 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 empty for that stack. All right, so struct instructions. So what are instructions then? So let's do this. Let's do this as well. Yeah. So instructions are basically like stack, but we won't be writing to that container, right? It should be read-only. And by the way, let's implement a couple of instructions. So we'll be having a no-op instruction, that's for sure, and something like push T instruction, right? And T is, of course, phantom value as well, right? So no-op instruction does nothing to our state machine, but it will, advance the stack pointer by one, right? And push will actually like take this T, whatever this is, and push it onto the stack, something like this, right? So yeah, and the way all computations work is something known as fetch and execute cycle, right? So basically, by the virtue of having the whole program and the current instruction pointer, we should be able to fetch the instruction, the current instruction that we will be executing, right? And once we've done that, with that instruction on hands, we should be able to execute it, right? So hence fetch and execute cycle. So let's model that with a trait. So trait like fetch, right? And the result, and not the result, but the associated type, I would say. Here, I should represent a current instruction, right? So impl like fetch for something like yeah, something like instructions, and we have like 8 of them, right? Like 0, I0, and something like this, right? And 0 is not implemented because, well, numbers, and use numbers this, right? So this fetch thingy will be implemented for tuples which contain the instruction set, or basically like the current program and the current instruction pointer. So if the current instruction pointer is 0, we should be returning the I0 from here, right? So let's go ahead and implement a couple more. So 0, let's go ahead and say 1, right? So I1, and 1, so it's like 2 now, I2. So it's like 2, right? Yeah, 2, 3, I3. 3, so 4, I4, and I think I will be needing all the way up to 5, 4, 5, right? Should be, oh, I5, I guess. That's that. And now when we have that sorted, we need to implement, like define and implement the exec trait. So trait exec, right? And like type UVM state. So impl exec for that state, like stack instructions and instruction pointer. Exec for I want to do this, so like nope stack instructions and instruction pointer, and type new stack, a new state machine, and should be like successor of instruction pointer, I guess. And I don't need that. So when the no-op instruction runs, it doesn't do anything to our system, right? The only side effect is advancing the instruction pointer by 1, right? And let's go ahead and implement the push instruction, right? So I think now we actually need a bit more details here, and that, yeah, like stack, but it's like 0, 1, 2, 3, and the stack now should be t as 0, as 1, as 2, right? So when we push t onto the stack, which previously was this, the result should be that. Straightforward enough, I guess. All right, so when we have these, like the fetch operation implemented and execute operation implemented, let's go ahead and implement the kind of, next state, or I don't know, step for the virtual machine, right? So impl like VM state stack instructions, instruction pointer, right? Public function step self, and whatever we are returning here, I know for sure that we won't be doing any runtime stuff, so that can be, substituted with to do, so no problem here. Okay, so it's like stack instructions and pointer, right? So first we can actually get the instruction out of our instruction list, right? So it's like instruction, yeah, it's like instructions and instruction pointer as fetch, right? Instruction. And that trait is not implemented. Let's go ahead and make sure that we can run it only for stuff that implements that, right? And now when we have this instruction here, you can actually execute it. So stack instructions and instruction pointer as exec new VM state. And yeah, looks like it. And that bound is not satisfied as well. Let's go ahead and satisfy it. So let's see how it works. Okay, just give me something. I think it's like this. Yeah. Not like that. So let's go ahead and create a stack. Like empty, 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 empty. The program should be like instructions. Nope, 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 nope. So how many? 1, 2, 3, 4, 5, 6, 7. And another one is nope. Cool. So we've created this virtual machine thingy, right? Which has type initial virtual machine, basically, right? And now we have this step thingy. So let's go ahead and do this, right? And you know, that program is not particularly interesting, right? It's just a bunch of knobs, but you can see here that nope actually does advance the instruction pointer. So kind of works. Let's see. Step again. And another knob gives us the successor thingy in our instruction pointer. So it works, right? So let's do something more interesting, maybe like let's do push 1, push, I don't know, maybe like 2, right? So now not only the instruction pointer should be changed, but also now we have the 2 and 1 on the stack, right? So we pushed 1 and then we pushed 2. Now 2 should be on top of the stack, and in fact it is, right? So let's go ahead and implement an add operation, right? So what add supposed to do? Oh, let's see. I think I can reuse this to implement add. So we have this, I don't need t. I have that, and then be like add as 0 as 1 as normal form. Normal form. And then should be like s2, s3, and empty, right? And of course that's add, or I guess add, right? And it doesn't like what exactly? Overflow evaluating, yeah. So probably it wants me to make sure that S0 and S1 are edible. Yeah, and it's happy now. Okay, so now let's go ahead and, you know, we have this 1 and 2 on stack. Let's go ahead and add them together and do one more step. So what we have on top of the stack is 3, and the instruction pointer is now 3 as well, right? So 0, 1, 2, 3. So the very next instruction will be null again. So what I'm saying, this looks like it works, right? Yeah, let's do like tests basic, right? And again, we're not running those tests because there is no runtime associated to that whole shenanigan. So tests. I wanna implement the jump opcode that will unlock the control flow for us. So jump, right? Let's go ahead and implement that. So like jump t, and it's like, you know, phantom that. And I also want to implement something known as dupe. So let's go ahead and implement dupe first. How do we implement dupe? I'll take this, right? So for dupe, right? When we have S0, S1, S2, S3, dupe supposed to take this as 0 and basically just stick it in here, right? And because we only have 4 entities in our stack in all times, then S3 should go. So yeah. Something like this, right? So this is dupe. And what about jump? Jump actually is similar to that. So jump t, and basically it should just substitute the instruction pointer with that t, right? So let's go ahead and see how it works. So I'll push 1, I'll dupe it, I'll add, and then I'll jump where? I'll jump to 1, right? So push 1, dupe, now we have 1, 1, then I add, now we have 2, and then I'll jump to 1 basically on that instruction. And then, you know, I have this 2, I'll do 2 duplication, so basically like 2, 2 again, I'll add them, now I have 4, you know, I'll jump back, and now I have this kind of progression going on that stack, right? So push, dupe, so let's see how dupe works. So we've pushed 1, we duped it, right? So it's 1, 1 now. Step, let's go ahead and see. So we've added those, and now we need to, yeah, now we you know, performing this jump to 1, and the stack pointer, the instruction pointer, sorry, should go to 1 again. Let's see if that's the case, right? Yeah, so the instruction pointer is 1 again. And now we can actually like do that in cycles, right? So the instruction pointer is 1 again, and when we have what we have on the stack is 1, 2, 3, 4 is 4 basically, right? And yeah, so that should give us 8, I guess. Let's see. Yeah, that should give us 8. So that's another cycle. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so that program works actually, right? So what I'm saying, you know, that computer kind of works. It's weird, but it works, and it doesn't require any runtime. It's all done in compile time. So let's go ahead and implement Fibonacci numbers, fib, right? And I will be using a specific kind of specific implementation for stack-based virtual machines, right? So the implementation I came up with is this. So I'll push 1, then I'll push 2, and yeah, let's go ahead and like remember what Fibonacci are, right? So it starts with 1, 1, and every next Fibonacci number is just a sum of 2 previous ones. So 1, 1, 2 is basically just a sum of 1 and 1, 3 is a sum of 1 and 2, 5 is a sum of 2 and 3, and so on, right? So I'll start with 1 and 2. So push 1, push 2. Then I actually need one more operation to be available, something known as rot3, which basically like rotates the stack, like does a cyclic rotation of a 3 outermost values on the stack. So let's see how that's supposed to work. So I'll take this, I guess. So yeah, rot3. Right, so when I have this, the result of it should actually be following. So it should be S2, S0, S1, and then S3, right? So we've taken this S2, and now S2 lives here, and everything else is supposed to be exactly the same, right? So basically this. Cool. So S1 is S0, S1, S2, S3, and now it's S2, S0, S1, S3. Yeah, that's what I want. So for Fibonacci numbers, I push 1, push 2. I do dupe here. Then I compute rotation 3. And then I do addition, right? And then I can actually go back to that dupe thingy. Like jump to that dupe, which is 0, 1, 2, right? And let's see how it works. So it starts with by like pushing 1 and 2. So now the stack should be, yeah, 2, 1 because of the order, right? Then I dupe it. So let's do step again. Let's see. I dupe again. So it was that, and now it's successor, successor. So basically, I took that and dumped it, right? So it's 2, 2, 1. Now I need to rotate it, right? So now it's 1, 2, 2. Then what's next? Next is addition, right? So it should be like, oh my goodness. Should be like 3 and 2, right? Yeah. And then I jump back to the dup, right? So this thing is exactly the same, but the instruction pointer is 2, right? And we're jumping to 2, and the result of it is instruction pointer equal to 2. So that first cycle actually worked, and on top of this stack, we actually have the value of 3 and 2, right? We started with 1 and 2, and now we have like 3 and 2. And now we can just proceed with those, like, with those steps in cycle, right? So now the stack, the instruction pointer is 2 again, right? So we've completed the another cycle, and let's see what's on the stack, right? So it's 1, 2, 3, 4, 5, and 1, 2, 3, right? So basically it's 3 and 5, right? And we can actually like proceed that again. So let's see. I think struct VM state. Yeah, I think we might be missing something somewhere. Current scope. Oh, it's not next. I'm sorry. I don't know why, but it's not next. So yeah, so the instruction pointer now is 2 again. And what's on the stack is 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5. So 8 and 5, and basically like these two, right? And yeah, as you can say, as you can probably tell, we are kind of crawling up that ladder and eventually, you know, we can get to whatever Fibonacci number. So yeah, I mean, that's that. I think this is pretty cool. Is it any useful? Probably not the stack-based virtual machines for Peano numbers. Probably that part is useless. But that kind of shows us like what can be potentially done within the type system itself, right? So if we can model the like stack-based computation purely as a Rust's type system construct, that would mean that, you know, some kind of more useful, let's call them, patterns, maybe like session types or something like that, should be doable as well, right? And that should not be a problem. So that's that. I hope you guys, you know, had some fun with that. I hope you guys find that as exciting as I find that, right? Because I find that to be quite interesting. And so yeah, I guess I'll talk to you next time, and bye.